Now, what are some things we can do to speed up a reaction or slow down a reaction? We call these reaction rate variables. And remember, to do our reaction, we need to achieve our transition state in order to go from starting materials to product. Let's review that we have our energy versus product of reaction, progress of reaction diagram, and whether a reaction is endothermic or exothermic, either way, you still need to go through some kind of transition state to have that product, have that reaction occur. And so what we need is a collision. If we have more than one starting material, we need a collision of those molecules to occur with enough energy to reach up to this activated complex, this where we're starting to form bonds and break bonds, this transition state. So what are some things we can do? Well, one thing we can do is we can increase the temperature. If you increase the temperature, we increase the rate. Now, this is true whether you have an exothermic reaction or an endothermic reaction. This is always going to be true. We speed up a reaction by heating it up. Well, what's happening there is if you heat up a reaction, you increase the kinetic energy of the molecules. In other words, they're moving faster. Now, if you imagine a solution with our starting materials stirring around in the solution, and you heat it up, and now they're all stirring around, they're moving around faster, what happens is when they collide, that is now going to be a high energy impact, and what you'll end up with is more collisions have the necessary energy to achieve the transition state. Okay, so our reactions are going to go faster the hotter the condition is. This is why certain reactions like food spoiling, that's going to happen faster at room temperature or faster in hot foods than in cold foods. That's why we store our food in the refrigerator. That's why maybe you store your batteries in the refrigerator or your medicines in the refrigerator. The colder you keep them, the slower all the reactions that might happen for degradation. Okay, another possibility is we can increase the concentration, and we can increase the rate. We just saw on the previous slide how that the rate expression shows the rate being proportional to the concentration of the starting materials. So if we increase that concentration, you increase the rate. Now, how is that happening? What we're doing here is we're going to increase the probability of having of collisions. So if you have more molecules in a smaller area, it's more likely that they're going to collide, and therefore a reaction proceeds at a faster rate. And finally, if there's some way to one thing I can point out for these first two to describe it is if you think of our molecules that are colliding as if they're bumper cars. Let's say we have two bumper cars that need to collide at a certain speed in order for a reaction to occur. Okay, so increasing our temperature is like having our bumper cars racing around a lot faster, and if they're racing around, then when they do collide, it's going to be a very high energy collision. If they're going very, very slowly, if we have a nice, cold temperatures, it slows down all our molecules, and so when those bumper cars do collide, they're going to do so very low energy, and that's not going to cause a reaction. So most definitely a relationship between temperature and rate. Increasing the concentration, if we think about our bumper cars, it's like having, let's say we have 10 bumper cars, and we spread them out all over the United States, let's say, and they're wandering around the United States. Now, how likely is it that they're going to collide? Very unlikely, and therefore it's going to be a very, very slow reaction if that reaction requires a collision. However, if we take those 10 bumper cars and we put them in the room with us, in our classroom, and have them racing around, well, of course, they're more likely to collide, and therefore a reaction is going to happen faster. So increasing the concentration is another way to increase our rate. And the last way to increase our rate is if somehow we could decrease our energy of activation, that would make it a faster reaction. So where was our energy of activation? It was right here. It was the energy required for our starting materials to reach this transition state energy. So if we could decrease the height of the hill that we have to climb, we could do that by somehow stabilizing, bringing the energy of the transition state down. By stabilizing the transition state. If somehow we could stabilize the transition state, that would be a faster reaction. Okay, how can we do this? Well, there's a few different things that we might find. It can be done with solvent effects. Certain solvents might be better at stabilizing a transition state than others. You could have steric effects when you have crowding. That's going to be something that maybe raises a transition state energy, or reduced crowding will lower it. That will make one reaction faster or another. What's another way? Have you ever seen a reaction diagram that looks something like this? Have you ever seen that picture where suddenly a different path is taken that's lower in energy? What did that? Perhaps if we added a catalyst, that would be a way that we can lower our transition state energy. So that would be the role of a catalyst, and of course catalysts are there to speed up a reaction. Okay, so all sorts of things can be used to decrease our transition state energy, and the key is that if we have a lower transition state energy, we have a faster reaction, and we're going to see lots of examples of this as we study organic reactions. So this is a concept that's really important to keep in mind because it'll explain a lot of the observations that we make in the future.